Welcome to the beginning of the last unit in chemistry this year, which is acids and bases. You're going to get a brief overview of what an acid and base actually are, learn how to do some neutralization reaction work, and at some point talk a little bit about the pH scale. But today we're going to really focus on what an acid is and neutralization. So there are two different definitions of acids that we go through as chemists, and they both tell you something a little bit different about the actual acid itself. The first definition that we're going to talk about is the Arrhenius definition, and this is the substance that when you put it into water, it basically increases the amount of hydrogen ion in solution. So an Arrhenius acid is something that increases the concentration of H plus in solution. And what happens is that if we take something like, I don't know, HCl, which is hydrochloric acid, and we add it to water, the HCl will break apart into the hydrogen ion and the chloride ion. So from the last unit in solutions, we talked about the fact that ionic compounds will dissociate into their ions, something like that. But what happens what especially happens with acids is that when they're in the presence of water, the hydrogen ion doesn't just kind of float around by itself. It actually bonds to some of the water molecules. So when it bonds to some of the water molecules, it forms a compound called H3O plus, and then we have in this case, the chloride ion left floating around. So in this case or instance, the H3O plus has a very, very special name. It's called the hydronium ion. And the hydronium ion basically is what we measure to determine how acidic a solution is. So any acid or any Arrhenius acid is something that you put into water that makes H plus available to create the hydronium ion. Now, the other definition that we're going to be talking about is something that's called the Bronsted definition, also known as the Bronsted-Lowry definition. The Bronsted definition is a substance that will donate a hydrogen to another substance. Now, in the case of hydrochloric acid, that's kind of easier to take a look at because it falls in the same category, the same definition. So here we would have water plus the proton from the acid, and I'm going to re-illustrate that in a minute, to create the hydronium ion. So you have to remember that hydrogen by itself has in terms of protons, it has one proton. It happens to have, in terms of neutrons, it has 0 neutrons, and in terms of electrons, it has 1 electron. That's a neutral hydrogen. But when you have the hydrogen ion, you have 1 proton, still no neutrons, and the number of electrons is also 0. So when we talk about hydrogen ion, we often refer to it as simply a proton because that's kind of what's left. So in the case of Bronsted-Lowry, or the Bronsted definition of an acid, it's a substance that will donate a hydrogen to another substance. So in this case, water, the example, plus the proton from whatever acid we're talking about, makes the hydronium ion. And in this particular situation, the Arrhenius definition and the Bronsted-Lowry definition appear to be the same thing. They're both increasing, they're both centering around hydrogen. Sometimes there is an instance where you will have water act like an acid, and it can also act like a base, which we'll talk about that in a little bit. So basically, we have Arrhenius acids, which are acids that increase the hydrogen ion in concentration, and Bronsted-Lowry acids, which are substances that donate a hydrogen to become, the donation of a hydrogen to become an acid. There are some properties of acids that you should be familiar with. They react with bases to neutralize them. They will change the color of acid-base indicators. They tend to have a sour taste. They will produce hydrogen gas when reacted with active metals, like in single replacement reactions, and their pH values tend to be less than 7. So some common examples of acids would be things like sulfuric acid, which are found in car batteries, nitric acid, which is used in the production of fertilizer, hydrochloric acid is stomach acid, citric acid is found in all of your citrus fruits. Phosphoric acid is the tangy or sour taste that's found in sodas. Acetic acid is basically vinegar, and carbonic acid is found in soda. It's just a form of that has to do with carbon dioxide. So those are some of your examples of your acids. Now, there's some bases that we have to talk about, and we have an Arrhenius definition of a base, and we have a Bronsted-Lowry definition of a base. An Arrhenius definition of a base is any substance that will increase the amount of hydroxide in water. So if I take something like sodium hydroxide, NaOH, and I put it into water and I allow it to dissociate, I will get Na plus 1 and OH minus 1. So that's the dissociation reaction, which we talked about last unit. But when we take sodium hydroxide, for example, and we put it in water, we have water, which sometimes we can write as HOH. So on the product side, we will have still water. We will have the sodium ion, and we will have the hydroxide ion. And when you take something like sodium hydroxide and you put it in water, it increases the amount of OH that's present. And the reason why I took the time to write hydroxide or water as HOH is to show you that that's where some of the hydroxide actually is located. So any substance that you put into water that when it dissolves adds more hydroxide to water is called an Arrhenius base. Bronsted-Lowry bases are substances that tend to accept a hydrogen from another substance. So the example below is an example where NH3 is ammonia. It's a cleaning solution or whatever, and it's going to be in the presence of a proton or a hydrogen ion from some unknown acid, and in that case it combines together to make the polyatomic ion NH4, which is ammonium, which is the ammonium ion. So in this case, the ammonia NH3 acted like a base because it accepted a hydrogen. So the Bronsted-Lowry acid, say HCl, that is going to give up a hydrogen or a proton. That hydrogen, in the presence of ammonia, NH3, the ammonia will accept that hydrogen and become the ammonium ion. So that's the difference between a Bronsted base and an Arrhenius base and a Bronsted base. So in the case, remember, in the case of the Arrhenius base, it's anything that adds hydroxide to solution, and in the case of the Bronsted base, it's anything that accepts a hydrogen from another substance. So those are two distinctions that you have to keep track of when we talk about acid-base vocabulary. Now, there are some properties of bases that we need to discuss. One is that they tend to react with acids to neutralize them. They will change the color of acid-base indicators. They tend to feel slippery, so things like your basic soaps are bases, and they tend to have a pH value greater than 7, and we'll talk about pHs next week. So examples of bases are NaOH, sodium hydroxide, and so basically anything that has a metal and hydroxide is a base of some sort. NaHCO3 is sodium hydrogen carbonate, which is basically baking soda. Sodium carbonate is what's found in antacid like Tums, and NH3 is ammonia. So what you can hopefully see is that the NaOH would act like a Bronsted, or would act like an Arrhenius acid or an Arrhenius base because it has hydroxide to give up, whereas ammonia would act like a would act like a Bronsted base because it has the ability to accept a hydrogen. And so the rest of this we'll talk about. The rest of today's lecture is going to be about neutralization reactions, but you should be aware of some of the basic properties of acids and some of the basic properties of bases. So, in an acid-base neutralization reaction, we have things that we call strong acids, and when they react with strong bases, they form some type of an ionic compound and water. So, an example would be strong acid would be something like HCl. In the presence of sodium hydroxide, NaOH, which is a strong base, and they are solutions, so that's aqueous. Okay, and so then when they switch around, they create an ionic compound like NaCl, and they create water. And I'm going to write water as HOH to sort of illustrate this point. So the NaCl it's an ionic compound that stays dissolved in solution, so it's going to be aqueous. And the water that's produced is technically liquid water, so it's pure. So when we talked about double replacement reactions in the solution unit, we talked about the three things that drive a double replacement reaction to occur. One was the formation of a precipitate, one was the formation of a gas, and the other one was the formation of water. So in this instance, the formation of water is what actually causes the acid-base neutralization to occur. So to sort of review about net ionic equations, I would say that my net ionic equation here is H plus plus the OH minus makes the HOH, which is the water, and the H plus was aqueous, the hydroxide was aqueous, the water is pure liquid. And so that's the net ionic equation. That's what drives this reaction. So then in this case, our spectator ions would be the chloride and the sodium. So these are our spectator ions. And like we talked about last unit, they don't really do anything in the reaction, but we still need to have them around. So acid-base neutralization reactions occur when we have a strong acid and a strong base, and they combine together, and when they combine together, they produce some type of ionic compound, also known as a salt, and water. Now, you're going to be asked to do some calculations with some neutralization reactions. So here's an example, and the first example says you have 65 milliliters of 0.1 molar hydrochloric acid, and it needed to neutralize 25 milliliters of calcium hydroxide of an unknown molarity, and your job is to determine the actual molarity of the calcium hydroxide solution. So the first thing that we have to do here is we have to write the balanced neutralization reaction. So in this case, I'm going to take HCl, and I'm going to tell you that that's aqueous, and that's going to be in the presence of the calcium hydroxide. So we have the Ca, which is calcium and the hydroxide. And that's also aqueous because it is a solution. And then I'm going to put that, I'm going to mix them, switch them around, and I'm going to get the calcium chloride, which is so the calcium chloride as a product, and the water, which is the H, and I'm still going to write it as OH to kind of illustrate the point as to where all these things came from. So now, in this instance, I see water is formed, so that's going to be my pure liquid. And I also know that calcium chloride is going to be aqueous. because if we go back to the solubility rules from the last unit, rule number 2 said that chlorides, bromides, and iodides are soluble in solution unless they're with silver, mercury, or lead, and calcium is not silver, mercury, or lead. So this reaction checks out. It is a neutralization reaction where we produce water, which is something that we're trying to find, and that to drive the reaction, and a salt, which is the other thing that occurs. So then what I'm going to have to do is balance this equation, and I see that I need to put a coefficient of 2 in front of the HCl, and I need to put a coefficient of 2 in front of the HOH, in front of my water, and so now that's balanced. So the other thing that is important to understand about these types of reactions is that at neutralization, and this is something that's going to be new that you need to pay attention, is when a substance is neutralized, the moles of acid are equal to the moles of base. So at neutralization, moles of acid equal moles of base. So in this particular case, I need to determine the amount of the moles of acid that I have in order to figure out the concentration of the base. So the first thing that I'm going to do is I'm going to find moles of the acid. So moles of acid, we're going to use the molarity formula. Molarity is equal to moles over liters. We know the molarity of the hydrochloric acid is 0.1 molar, so I'm going to plug that in. And we know the volume is 65 milliliters, but we have to change that to liters. So 65 milliliters to liters is 0.0650 liters. So I'm going to put that in here. And when I calculate this out, I take the 0.065 times 0.1, and I get the number of moles to be 0.0065, need to have 3 sig figs here, 0 moles of HCl. So the next thing that I need to do is, for say step 2b, is convert moles of acid into moles of base. So in this part of the problem, what I'm going to do is I'm going to take the 0.00650 moles of HCl, and I'm going to convert that to moles of base using the mole ratio in the chemical equation. So I see that in the balanced chemical equation I have 2 moles of HCl, and I have 1 mole of base, which in this case is CaOH2. So 0.0065 divided by 2 gives me 0.00325 moles of CaOH2. So that's the amount of base that's actually in the solution. So the next step, which would be, say, 2C, is I'm going to find the molarity of the base. So which I'm going to use the molarity formula is equal to moles over liters. And this time I know the number of moles to be 0.00325 moles. And we are told that we have 25 milliliters, which we have to convert to liters. So 25 milliliters in 1 liter, there's 1,000 milliliters, so that gets me like 0.0250 liters. So I'm going to plug that in. So I'm going to divide those out, and I get a molarity of 0.1. And so in this case, it looks like I'm supposed to have 3 sig figs, so 0.130 molar CaOH2. So that's the work that's required to figure out this type of problem. So in this problem, the example here, we know the concentration and volume of the acid, and use that to find the molarity of the base. So that's this type of problem. Okay, so now we're going to do one more final example. And in this one it says, what is the volume of 0.5 molar KOH needed to completely neutralize 75 milliliters of 0.125 molar HCl? So again, we have an acid and a base. So I'm going to start with writing the equation, just like we did last time. Write the balanced neutralization equation. So I'm going to take my acid, which is HCl, and it's a solution. And I'm going to take my base, which is KOH, potassium hydroxide, and I'm going to mix them together. And hydrochloric acid is a solution, the KOH is a solution, and on the product side, I get HOH, and I get KCl. So I know that HOH is liquid water, and I know that KCl is aqueous because of solubility rule, actually number 1 and number 2. So in order to balance this particular reaction, it's pretty easy. It's 1, 1, 1, 1. And so again, I'm going to go through the same process. The first thing I'm going to do is find moles of, in this case, acid. So we know that molarity is equal to moles over liters. We know that the molarity here is 0.125 molar. We're looking for moles. And the volume is 75 milliliters, which I have to convert to liters, so 0.0750 liters, because it was 75 milliliters, 1 liter, 1,000 milliliters. Okay, so we get 0.0750 liters. So I'm going to take the 0.0750 times 0.125, and I get, in this case, the number of moles to be 0.009. We should have 3 sig figs here, so 938 moles of HCl. And then step 2b is to convert moles of HCl, moles of acid, into moles of base. And when we do that, we are going to take the 0.00938 moles of HCl. And the mole ratio here is 1 mole of HCl for 1 mole of KOH, so it's 1 mole of HCl for every 1 mole of KOH, which tells me that the moles of KOH here is going to be 0.00938 moles as well. So then the last thing that we have to do, is to calculate the molarity of the base. Oh, hold on a second. Or not the molarity of the base, we have to calculate the volume of the base. That's silly. Let me fix that. Calculate the volume of the base. Okay, so we're going to use the molarity formula again. Molarity is equal to moles over liters. And we know the molarity because that was given to us in the problem. So we have 0.500 molar KOH is equal to, and we know the moles, which is 0.00938 moles of KOH. And we're looking for liters of KOH. So in this problem here, we're going to have to solve out for liters, and you basically end up taking the 0.00938 divided by 0.5, and you get a volume of 0.0188 liters is equal to the volume. So that's roughly 18.8 milliliters if we move the decimal back. So that's how we would solve that problem. Now, some of you may or may not have struggled a little bit with how to get with how to calculate the liters on the bottom here, and I'd like to show you really quickly, just so that you remember. If we take molarity and moles and liters, we put it into the old triangle of fun. Oh boy, that was pretty bad. Let's do a better triangle here. Also bad. Also, it's best it's going to get, I guess. So, moles over liters. So in this case, the triangle of fun says that if I'm solving for, say, something like liters, and I cover up liters, it tells me I take moles divided by molarity. And that's how I came up with that particular math relationship there. Okay, so all you have to do is finish taking notes here, and then go ahead and on Monday we are going to work through a worksheet with us. So if you have any questions, let me know. Otherwise, have a good week.